Okay, so dam sandwich. Here it is. The dam sandwich and a changing side salad of vegetation along the riparian corridor. Or maybe a more helpful title is this one, Sediment and Vegetation Change on the Lower San Juan River in southeastern Utah. And I just want to acknowledge my co-authors. We've actually published the preliminary piece of this work in a Utah Geological Society publication. I'm an ecologist, but my co-authors are geologists. And so Gary Giannini is the master of the title. That was his idea, not mine. And our former undergraduate student, Logan Hartle, shown here hiding because he's so embarrassed by that weird title. Logan is now graduated and moved on to work in water resources, so that's exciting. So, what the heck am I talking about? When we think about dam impacts, the impacts of dams, we usually are focused on what's going on downstream. We think about changes in sediment load, we think about changes in flow regime, flood magnitude, flood frequency, things like that. Lack of scouring power to change the sediments along the riverbanks and to impact vegetation. But what about the impacts upstream of a dam? And I don't mean in the reservoir, obviously. Right upstream of a dam you have a reservoir, but upstream of reservoirs. That hasn't been looked at quite as much. And we've spent a lot of time on the San Juan River, and naturally you're sitting there in camp at night and you start, well, if you're a nerd like me, you start asking questions like, what's going on here? So we have a lot of interesting questions that have started to come up after spending years and years on the lower San Juan River. So here's the watershed, the San Juan River watershed, starting up in the high San Juan Mountains and flowing down into Lake Powell before the confluence with the Colorado River. And it does indeed have a dam sandwich. Look at that. Upstream you have Navajo Dam, and downstream, much more photogenic, the Glen Canyon Dam, which, as you know, forms Lake Powell with its famous bathtub ring in this picture. So interesting questions arise when you're working or looking in an area that's sandwiched between two dams. And many of our rivers in the West are like this, but the San Juan is one I just happen to be more familiar with. So after years of observations on the San Juan River, we've noticed some pretty substantial changes in the vegetation, in the riparian vegetation in the riparian corridor. And also some interesting changes in river behavior. For example, some small rapids that have just sort of disappeared in the last decade or two. And so that really has made us wonder about sedimentation, patterns of sedimentation, because my husband is a geologist and he can't help it. So we started wondering if sediment wasn't really accumulating upstream of the reservoir in the lower part of the river canyon and into the San Juan River channel. Has anybody here rafted the lower San Juan River down to Clay Hills? Only one of you? Oh. Well, don't go. You'd hate it. It's ugly. But so if you had rafted that part, you might say, yeah, I know about that sediment in the channel. There's a lot of it. It's kind of hard to find your way for the last few miles. So if sediment is accumulating in the river channel, the question arises, well, how much? How much sediment has accumulated? So, hypotheses, very scientific process here. We have accumulated lake sediment in the lower river, and we assume that has raised base level for the river channel. And that has resulted in a decrease in the stream gradient and therefore a decrease in stream velocity. And those processes, we hypothesize, are driving upstream sediment aggradation. And we think that that's happening even above the upper levels, the highest level of lake sediment deposition. And I'll try to explain what I mean by differentiating between those. And that is where we come into this changing side salad. So I'm interested in the vegetation aspect, and that's really driven by this underlying template of what's going on geomorphologically in terms of sediment accumulation. So here's the reach of the San Juan River we're focused on. This is the lower San Juan above Lake Powell there on the left. And we're down below, downstream of the famous goosenecks of the San Juan River, so downstream of the town of Mexican Hat, those areas that you might be familiar with. The blue circles on this map represent river miles, with river mile 0 being way upstream at Sand Island, which is near the town of Bluff, Utah. And Clay Hills is the most downstream boat takeout at river mile 82. The red circles represent places where we collected data on sediment accumulation. So what we needed to know to really undertake this effort, needed to understand a little bit about sediment deposition in the lake. And the San Juan River is super muddy, as are most of these big exotic streams coming out of the Colorado Plateau. Estimates are that 30% of the sediment deposition into Lake Powell comes from the San Juan River, even though there's a dam upstream. So most of that sediment is coming in below Navajo Dam. We need to understand the history of Lake Powell. When was high pool level met and how high was it? The previous elevation of the river channel, which could be a little tricky given that it's been modified so much by dams, but we turned out to be lucky in this regard. And then what we really needed to be able to measure was the current elevation of the river channel. So here's a picture of the San Juan River flowing into Lake Powell, and you can see that beautiful delta. And that's what we presume happens when you have a reservoir with a muddy river flowing into it. A delta is going to form, and you're going to accumulate sediment at the upper edges of the reservoir. This picture is from 2002, when the lake had dropped very, very substantially, as you probably know. But presumably when the lake was higher, similar processes were operating, so you had sediment being deposited into the upper levels of the lake. And the question is, where was that when the lake was at its highest? So it took 20 years for Lake Powell to fill all the way. And by filling all the way, I mean they were putting up plywood on top of Glen Canyon Dam, right? That's the conventional wisdom anyway. That in 1983, we had a huge El Nino year. This one is supposed to be like that. I don't think it is, but huge El Nino year, big flows coming out of the high mountains and big snow melt. And that's when Lake Powell reached high pool level at about 3,700, just over 3,700 feet above sea level. And then to go with that, we need some survey data. And fortunately, in the 1920s, the USGS was sending out survey trips to all of these river canyons. They were actually already surveying in the 1920s for dam sites, interestingly enough. And so the Trimble expedition included a guy named Hugh Miser, a geologist, and he spearheaded the survey and described the geology of the San Juan River canyons, which you can read all about in this fascinating document. And here's a picture of Hugh Miser in 1950 that happens to be taken by my grandfather. Kind of cool. So there was a survey in 1921 of the elevation of the river canyon on 5-foot contour intervals. So that's pretty good survey data going back to the 1920s. And I don't have fancy, expensive LiDAR data, darn it, so we'll rely on this. Then in 1986, there was a survey of the Lake Powell sediment, and trying to understand how much sediment had accumulated in the lake bed. So 1986 Ferrari survey. So we've got some really useful survey data to build on. So that's what this looks like if you plot it. The reddish-brown squares represent the stream profile taken from the Miser survey, with upstream being on the right and downstream being on the left. I know that's just the way you do river profiles. Sorry if it looks backwards. And then the purple represents the depth of the elevation of lake sediment in Lake Powell in 1986, so shortly after that high stand event. So now we've got that to build on, and we know that maximum pool level of the lake was about 3,700 feet elevation, and based on the Miser survey data, we know that that occurred at about river mile 70. So that's useful information for us in trying to figure out where to start our study. For getting an idea of the current channel elevation, we use repeat photography, and really a useful tool for ecology, but also for, turns out, for sediment study like this one. We use the repeat topography data to define the thickness and the elevation of the sediment wedge that accumulated upstream of Lake Powell. And that allowed us to delineate what the new river gradient is. So coming back to the map for just a minute, we now know that high pool for the lake was at river mile 70, so we know we want to study things at least to river mile 70 and below. But we also know that in the early 2000s, the little rapid that used to exist at the mouth of Slickhorn Gulch disappeared. It was swallowed up, presumably by sediment. So we think there's sediment accumulation occurring upstream of that high stand for the lake. And so that lets us define where we should do this study. We want to include river mile 70. We want to include river mile 66, the mouth of Grand Gulch, where we know something funny is going on with sediment. And so what we did is we started the survey at river mile 64, below the big rapid on the San Juan River government rapid. We got historic photos from NAU, from the Klein Library. We have an incredible collection of historic photos, and it's really easy to waste days and days just looking at all of the fascinating photos that they have. The photo points that we were able to find, we relocated in 2012 during low flows in the late summer and early fall. That's all there. In 2012, everything was low flow, but that turned out to be useful for us. We found a measurable feature in each of the photographs and used that as a scale so that we could estimate differences in water surface elevation. And then we compared our data with the Miser survey data and the Ferrari 1986 lake bottom survey to estimate the total sediment depth that has accumulated. So let's look at some pictures. Here's the first one. This is just below Government Rapid. The picture on the left, 1955, is from a series of photos taken for a thing called Disney Boys, where they take these kids on fun adventures and take movies of them. So there they are, playing in the river. And then in 2012, there's Logan standing there with a 6-foot-long yellow Paco pad for scale. And the red circles indicate the same boulder we could identify in both of those photographs. And notice that it's there on the riverbank. It's not buried in sediment. It looks a little bit lower, or sorry, it looks a little bit higher above water level in 2012, but that's just because there's less water in the channel. So 600 CFS in 2012, 3,200 CFS in 1955. So no evidence of sediment aggradation here. We go downstream a little farther. Now we're just above the mouth of Slickhorn Gulch. And this pair of photos, or trio of photos, you're going to have to take my word for it, but in a higher quality image from the 1955 photo, you can really make out the boulders on the far bank. And we recognize the same boulders still present in the same location today. Again, no evidence of sediment aggradation outside of the river channel here. But remember, this is where I said the rapid is gone. So it looks like, we hypothesize at least, that sediment has been accumulating in the river channel at this point. So we go downstream. Unfortunately, we have to skip over a chunk of river. We couldn't find any good old photos. But we get down to the mouth of Grand Gulch at river mile 70.5. And here we see some pretty amazing changes. The photo on the left, I realized this morning that one doesn't have a date on it. That's about 1960. And the photo on the right, 2012. The red circle, it's really helpful to work with geologists sometimes. They're good for some good stuff. They recognize fine details in rock outcrops. And so they say, oh, I recognize that feature, that pattern of sedimentary bedding. And so it's circled in both of those images. And look at what a huge difference there is in the location of that red circle. The person on the right is holding a 10-foot oar for scale. And we estimate that 26.5 feet of sediment have accumulated at this location. Or there's a 26.5-foot difference in elevation of the water surface. The water at that point, when we took the photo in 2012, was like half a foot deep. So we ascribe most of that difference to sediment accumulation. Downstream a little farther, river mile 76. the mouth of Old Jato Canyon, moonlight water, beautiful place. We have 3 photos here. The upper one from 1961. That's the year I was born. People were down there rafting and there was no sediment. The red circle is on a boulder that's perched way up on the cliff there. And we can identify that same boulder in this pair of images from 2009, 2010. It's the same rock, same location. We have, ready, 49 feet of sediment accumulation. Crazy. Downstream a little farther, now we're just above, or just below, excuse me, Steer Gulch, another tributary of the San Juan, getting down close to the takeout at Clay Hills. Again, using sedimentary features in the cliff face and recognizing the same feature in both the historic photo and in the 2012 photo, we're able to go to the cliff, measure a section of cliff that we can identify in both images, and come up with an estimate of 60 feet of accumulated sediment at this point. So we're just filling up the San Juan River Canyon with mud, basically. At Clay Hills Crossing, that's the boat takeout. That's the end of the line. If you're rafting down the river, you don't want to go any further. I'll tell you why in a minute. We didn't really have good photo pairs. So for this location, Gary and Logan got some surveying equipment, and there's a benchmark there, and they did some careful surveying, and we feel really good about this sediment depth estimate of 71 feet of accumulated sediment. Mostly lake sediment, but probably some river sediment as well. So there's what it looks like. This is what our new profile looks like. Or actually what this is showing is the change in channel height, or the thickness of accumulated sediment as we go downstream. So upstream, river mile 64 there on the right, with no sediment accumulation at the first sites, and then more and more thicker and thicker sediments accumulating as we went downstream until we get to Clay Hills with 71 feet. So we presume this is a combination of lake and river sediments, and we think it's probably being driven by a feedback between lake-driven rise and base level downstream that's, slow, as I mentioned earlier, slowing stream velocity, and driving this continued sediment accumulation upstream. So we've got this cool idea of the creation of sediment wedges, with the lake sediment wedge that thickens downstream, and superimposed on top of that river sediment wedge that thickens upstream. Here's what it looks like. Here's our nice blue, pretty Lake Powell at high stand, with the highest water level at 3,700 feet elevation. And based on the Ferrari lake sediment survey, we can estimate the depth of lake sediments that have accumulated. And then when we take our survey data and superimpose it on top of that, we can estimate the thickness of the river sediment wedge. Pretty cool, I think. But this really raises kind of an interesting question about reservoirs in general. Why the lake level has dropped a lot since 1983, since high stand. So why is base level still high? Why is sediment still accumulating? Normally you would think the river would start down cutting and carrying that sediment back out further downstream. Well, here's why. And here's why you have to get out of the river at Clay Hills. Excuse me. There's a waterfall downstream. And so when the lake dropped, the poor San Juan River is wandering all over trying to find its old channel. Can't find the old channel, so it makes a new one through the unconsolidated lake sediments, but then it periodically will hit a bedrock ledge. And it hit one in 1993 and formed this first waterfall, this one on the left, which we inadvertently ran because nobody knew it was there yet. That was exciting. It wasn't that big. And then the lake came back up, buried that waterfall, has dropped again. And now there's a new waterfall flowing over that bedrock. You can see the layers of bedrock there. And it's about 15 feet tall. So that's maintaining this, we presume that's maintaining this artificially high base level and allowing for sediment accumulation upstream to continue. So the most important part of this is what's going on with our side salad. So it's really interesting. The vegetation patterns do, in fact, coincide with the patterns we see in sediment accumulation. And you should go see, I'm going to put in a plug for my student, Summer Morris. She's got a poster still up out there. She looked in more detail at the sediments. I'm going to steal her thunder a tiny bit, but you should still go look at her poster. So there's not just a difference upstream and downstream of the sediment aggregation area. We actually see 3 distinct zones of vegetation, and this is what Summer found in her work. So this was a neat surprise. We have pretty good indicator species, plant species, for the different sediment types. Upstream, where we have no obvious sediment aggregation, the vegetation is a little more diverse, more diversity of forbs, a lot more open bare ground. The river sediment wedge, so just downstream of Sicorn Gulch, we have a unique mix of Phragmites and Baccharis. Those are the indicator species for that sediment type. And then once you get further down, and primarily on lake sediment, it's a tamarisk-dominated vegetation type. So what's that look like? Here's the tamarisk, and it's defoliated by beetles. You can see it yellow in the background, with a little bit of Baccharis in the foreground. Well, maybe a lot. But this vegetation type seems to be driven by the influence of the downstream dam. And then another interesting thing that I would really love to look into in more depth is what's going on as a result of the upstream dam. Remember, Navajo Dam is still up there. We have definitely seen a huge increase in vegetative reproduction of Salix exigua, coyote willow, just armoring the banks in some places, much higher than historically. And presumably this is a result of the lack of scouring floods because of the upstream dam. So, good old dam sandwich. So, in conclusion, the dam sandwich has interesting implications for sedimentation. Aren't you hungry? And has also led to a diverse and changing side salad. There you go. Really corny. So I just want to acknowledge research permits we got from the National Park Service to work in Glen Canyon Recreation Area, and also the permission granted to us to use those historic photos from the Klein Library, and funding from Fort Lewis College for student research grants, as well as faculty research. And there's old Jato Canyon before the sediment accumulation. It's now there's sediment up to here. So, thank you. And I'm sorry that wasn't really an applied restoration talk, but it's cool. Questions? Oh, just talk loud. Just talk.
The bedrock ledge that the river is now flowing over, or more recently is flowing over, did the river evolve to that new position, or was that ledge always a waterfall?
No, there was never a
There was
never a water. So the river evolved out of its old channel.
That wedge forced it to go over and find a new base level.
Yep. And there's so much unconsolidated lake sediment out there. It filled the old channel completely, and now all bets are off. So maybe a quick question. One more. Okay, good.